Are you able to set it?
Yes, I will.
And by pressing a button, you're able to move the.
Yep, I'll definitely go. Yeah.
And it is recording, right?
Yep.
Hello, good morning. Present. New homework that has been posted. New. Tuesday. Thursday. following Thursday, that is September 15th. Yeah. Since this is going to be your first midterm in this course, even though you have those who has taken the course with me in the first semester, the format should remain the same. One thing I would like to stress is that earlier last semester, at the end of the semester, I had dropped the homework for those who had a higher average in the exams over the homework. There is no such plan for the semester as of now. I'll see as it goes, but for now it's not there. And I do see a couple of you guys who are not doing the quizzes and homework I'll see today. So make sure you're not in that group. So do try the homework and the quiz. Regarding the exam, the best way to go is as a collection that you can form using lecture examples, homework problems, and solve exam, right? Examples. I don't mean the problems, examples in textbook. What if one feels that this is a small set, that means you're not, most probably you're not going through the problems on your own and you're depending too much on the solutions or on the notes. So work it out on your own, and often you feel that you're stuck at how to set up the problem and so on. And you make mistakes, and I personally feel that mistakes are the best way to study, because then during the exam, you know that that path cannot be taken. Like while you're working on a problem, you work, let's say it's a matter of algebra. There might be 3 ways to do that algebra. 2 ways might be too long a procedure, and one might be very short. So you want to learn that by doing the homework. So that's one recommendation. This often works anything that involves a lot of algebra or mathematics in general. So that's an advice. We have an exam on Thursday. When you took the exam last semester, if you took it with me, then that was a 15-minute exam. So this is a 75-minute exam. So accordingly, the number of questions will increase by about 1 in each probably. So there might be about 9 questions, 8 to 9 questions instead of 7 to 8 questions earlier. So be prepared for that. Any comments or questions you can think of regarding the coming exam? If you feel comfortable with the topic that's going on and you can read the homework problem and immediately phrase it mathematically, that should be a good preparation for exam. So that's one way of okay. We introduced the idea of electric charge, the associated electric force, and we also introduced the idea of electric field, which should be very new, even though it is very similar to the gravitational field that we have already come across before. Here we are quantifying things a lot. So that's the main idea we have introduced. And we introduced the idea of electric field lines very qualitatively. Like we talked about, electric field lines are a measure of how strong an electric field is, which is in turn a measure of how strong an electric force is. But now we want to quantify it. How big is it, and especially how do we know if there is a charge in the vicinity or not? So let's talk about that. Just a summary. You've all seen vectors, so vector, and now we have introduced something called vector field. An example is example is force is a vector versus electric field. That means what is the vector versus vector field? A vector is just one quantity like force. It has three components and that's it. Electric field has three components, but it is defined at every point in space. Force is just three components. Electric field is infinite components in the sense that there are three components at every point in space. It is defined everywhere that you can imagine. And that's the only difference. Electric field at a point in space is the measure of the force that is exerted on a charge. So that would be the mathematical connection between the two. And then we talk about electric field lines. Electric field lines is a way to intuitively see the idea of an electric field. So let's think of a point chart. We already talked about single point chart, double point chart. So just for an illustration, let me try to draw here three electric field using 3 point charges. Let's say this is on at the corner of an equilateral triangle, and all are possibly charged, and this is charge Q, and charge Q. Think of forces. This repels from these two. That means electric field anywhere down here will be to the top. So somewhere here, if you keep a force charge, it will repel from all three, and the electric field lines will be this way. So that will be the electric field lines. That will be the electric field lines. Electric field lines, remember, is the force a force charge, not any of these three charges. These three charges are fixed. A force charge would experience if you keep it along this line. It gets weaker as you go, but for now, we are saying just direction. If you were to keep it along this bisector lines, again, this force will be in this direction, there will be a force in this direction, and this will repel. But the vertical component will add, and the horizontal component will subtract, and there will be the two. And the same thing will work. And remember that electric field lines cannot intersect. So if you had a point charge, then you already coming out. Now that they cannot intersect, so they cannot go in, because if they go in, somewhere they will come out from, and they're already the electric field lines from here. So they have to squeeze together, and the lines, the way they work out is that takes a little thought, and but it's not, once you see it, it is intuitively clear that that's what will happen. So that's, so they squeeze towards each other, but then eventually they have to. And the same idea here. And it seems like there are no field lines in the center, but that's not true. That's not completely true, at least right at the center. So there's few lines, very few lines can go in, and the stuff they don't have to, they look like this. And few points that, let me draw two more. If you notice, these points will have electric field 0. And right at the center, just because of symmetry, the forces have to cancel, but also will be zero. But I had told earlier that electric field lines should not intersect. Do the electric field lines intersect right at the center? They seem to be intersecting, so that needs to be something off from what I said before. But the point is electric field is zero. So if it is zero, really the intersection is not really relevant because they are coming and going to zero. So this is first comes back that electric field is zero. It's like a vector right at the origin. If you have a central symmetric vector field, what is that? Vector right at the origin, if it's magnitude is zero, it doesn't really have a direction. Like at the north pole, if you want to talk about in what direction will a magnet go right from axis, it is not clear along which direction it will go. So, so that's one point. That is also another feature that it seems like there are all these field lines that are converging in there. That's not completely true, but because this is a three-dimensional picture. A plane is selected in here. These three charges are spectral, and that plane that contains that charge is spectral. So you spoil the symmetry in that sense, and the field lines from here will come out. So there are field lines that are coming in and they're coming out. So if you were to enclose this point here, not all lines are going in. Many of them are coming out. It's just that it's not visible in this plane because they are coming out of the plane. So field lines go, the E lines come out of the page at the center. This comes out to be an important factor once you realize what the electric field is, what is the property of an electric field at the origin, which we are going to talk about today. I drew this very qualitatively, but one would like to know, is there a quantitative way of doing this? How do we know that these field lines are here? Of course, we can do the mathematical calculation or integration and get this. It's tedious, but are there some qualitative features which you can grasp much more easily just by looking at this distribution? So that involves the idea of electric flux. Electric flux is a measure of how many electric field lines are crossing a certain area. It is a measure of field lines crossing an area. Let's do an example. We have already remembered just for so if we have spherical symmetry. By spherical symmetry, I mean anything which is the same everywhere on a sphere. A point charge is a classic example. So point charge. That means what I mean by spherical symmetry, whether I'm here, as far as I'm equal distance from the charge, even coming out of the board, everything looks the same. The force on a third charge or second charge will be exactly the same. And we said the electric field due to that is K times Q over R squared times R factor. That's the information that this is actually radially outward, which is the idea of a sphere. Think of a sphere here, and then close. Whether you're standing on the sphere here or here, there is no way you can make out the difference just by measuring the electric field. You might be able to look at the stars and say you're in a different place, but electrically speaking, just because of the point charge, there is no asymmetry anywhere on the surface. The other example we will talk about is planar symmetry. And that is for planes. The best way to have an analogy is that if you have Earth, if you're very far away from Earth, Earth looks like a sphere. But if you come very close to the surface of Earth, that means if I'm standing on the surface of Earth and measure what is the what is the gravitational field, it's 9.8 meters per second square. It is constant. So everywhere on the surface of a plane, Earth is practically a flat mark if you want, if you're very close to the surface of Earth, and in that limit, that is a plane, and in that case, the electric field is positive charges on a plane, and the electric field lines are coming out like this, and they are uniform. Gravitational field is a constant on the surface of Earth because it's practically flat. And similarly, the electric field lines for a plane is simply sigma over 2 epsilon naught times, let's say this is the normal direction, that's the normal direction, and that's n hat. And hat is a symbol that tells that it is perpendicular to the surface of the plate. And sigma is charge per unit area. That gives you the dimension clearly, charge per unit area, charge per length square, that is that's dimensionally, that gives you that factor, and this has a 1 over epsilon naught here, and that's the 1 over epsilon naught. Why, if you write this in terms of k, this comes out as 2 pi times sigma, and why is there a factor of 2 pi? People are asking why is there a factor of 4 pi in the surface area of a sphere. One, at least I know only determines that using tedious mathematics. One point here is that this is for an insulator. We emphasize that, and in your homework you will see this distinction coming again. If this was a conductor, so that means if it is a conductor, means the positive charges are free to move versus they are stuck on the plate. This changes a bit, and that is sigma over epsilon. And that factor of 2 you can associate with, if it was a conductor, there is no electric field inside the material, and electric field is 0 there, which we will be able to see and have a better feel for it after we see electric flux. So that's the 2 configurations we'll talk about. Also, the semester we will try to work confine our attention to spherical distribution and planar spherical symmetry and planar symmetry, primarily because you can stay without calculus there for quite some time. In the classroom, I will do cylindrical geometry also, but for spherical geometry, they are concentric. It is possible to work with algebra alone and not worry too much about calculus, but the calculations are not tedious. So coming back to electric flux, let's talk about planar symmetry. That means to say the electric field lines are uniform, so that's the constant electric field. And this is easier. One should always imagine that there is somewhere to the left there is a positively charged plate, Which exactly like that, and somewhere on the right, there is a negatively charged plate where the electric field comes and end. Electric field always originates on a positive charge and ends on a negative charge, or they come from infinity and go to infinity. If you were to keep a positive charge here, if you imagine there is a positive plate, they will repel and they tend to flow along with the electric field. A negative charge flows against the electric field, it finds the electric field, and a positive charge just falls in an electric field in the sense that it flows along with the electric field. So that's one physics associated with it. But what we want to now talk about is something called flux. So let's have an abstract area. So this is a volume I have put in here. An abstract, that means to say that there is nothing real in that box there. This is just for our thought purposes. So this is an abstract box. Often this is called Gaussian surface. And so again, this is a box that's a cube in a sense. So there is a surface on the left, there is a surface on the right, there are two surfaces on the top and bottom, and facing the board and on the back side of the board, there are two more surfaces. So there are 6 surfaces of this box, and let's have this labeled as 1, that's labeled as 2, that's labeled as 3, and that's 4, and there is a 5 and 6 coming out of the board on the 2 sides of the blackboard. I introduced the idea of an area, so let's remind ourselves that this is an area or a surface area. Let's think of a flat surface. So this is somewhere in space, that is a tiny element of a surface, and now let's say this is area is dA. It's a tiny element, that's why I'm calling it dA. Small or infinitely small area element. That means to say that this could be part of a bigger surface. Think of a small element of a sphere. On the surface of a sphere, you take a small chip on it, and that's area. And at this point, I should ask: is area a scalar or a vector? I must have asked this before. Scalar. It's a vector, okay, and that will play an important role in this, at least in the chapter for sure, and in general in the whole course. Area is not a scalar, it's a vector for our purposes. It's true that whenever we think about the surface area of a sphere, we always say it's 4 pi r square, but that's adding up all tiny elements of vector area, and it is a magnitude that is added up. Area itself is a vector, and its magnitude is the area itself. So area is a vector. So area is a vector. And for our purposes, there are more concrete ways of defining the vector associated with it. Area for our purposes, we need to think about magnitude and direction. We don't have to worry about the X and Y component. We need the magnitude of area. Magnitude is what we are already familiar with. It's just that we have to take it back to the infinitely tiny element and not worry about the complete area. So the magnitude is the area itself. That's the standard area that we think of when we think of a plate. That's the area itself. And then comes the direction. That might be the tricky part. What's the direction associated with an area? It is perpendicular to the surface. Whenever you think of a surface, there is a unique direction that is perpendicular to it. But except for the fact that it could be going up or down. Right? If I were to say this is the palm of the surface is my palm, a vector that is perpendicular to that, that's the direction of area. You will immediately say, oh, that's also perpendicular to it. So that is an ambiguity in there, and we will take it away in a minute or so. So direction is perpendicular to the surface or normal to the surface. Perpendicular or normal. Normal to surface. So area is a vector, magnitude is the area itself, and its direction is perpendicular to the surface. And also, out of the two directions that is possible that are perpendicular to the surface, think of whether this is forming a closed surface or not. Think of this as a sphere. This is forming a, if it is curved on one side, there is a chance that it will enclose something, and it is coming normal, coming out of the surface. Out of the closed surface. If by any chance we are talking about a situation where it is not clear which way it is closed, especially for a flat surface. So if you were to draw, that's my z-axis, let's say. Sorry, this is my xy plane, and there is a tiny element here, and its normal vector is perpendicular to that. But then you would say, oh, why not that side? There is an ambiguity for a perfectly flat plate. You cannot live without that. So in that case, choose any one that suits you. It doesn't matter. But be consistent. Don't switch around in between a description. So once you choose the positive or the right side as the normal vector, be consistent with that. So there is an ambiguity if it's a perfectly flat plate. But perfectly flat plates are not completely true. In this case, for example, there is a positive charge somewhere here. So usually you say that, oh, there is a positive charge, so that will be taken as the closed surface. So electric field is enclosing that closed surface, or they are coming out of that surface. So that's for the area. Once we have the area, let's calculate that or define the electric flux. So the electric flux will be defined by the letter phi. So this is phi. 3/4 phi that's pronounced as PHI. That's the electric flux. There is a subscript of E there because later on we will talk about magnetic flux about a month or so later. And to distinguish that, we say this is the electric flux. This will be equal to break. First select any surface. So let's say we are talking about the electric flux about the surface 4. So this is. Let's say this is surface 4. It's the electric flux on the surface 4. The cube is consisting of 6 surfaces. So that's the flux coming out of surface 4. And that will be defined as electric field dotted. Remember the dot product between two vectors at every point on the surface, multiplying it with the area element. This is the area element. And this is on the surface 4. So this integration is done on surface 4. So you break the surface into tiny elements. Since when you're coming out of the board, it doesn't matter much. So that you break this into tiny elements, and each of them has a dA. Incidentally, dA is exactly parallel to the electric field. So remember your scalar product, it is cosine theta. So electric field is pointing, let's say this is X direction. That's your Y direction, and Z is coming out of the board. The electric field is in the direction of X hat. Area itself is also in the direction of X hat. I've written it in opposite ways. This is electric field is E times X hat. Area is X hat times the area. I've written it in the unit vectors in the opposite way so that the vectors come together. And the area integral is over the surface 4. And you break the surface into tiny elements, and you do this multiplication of the quantity that you're calculating for each element, and then you add up, right? That's integration. Integration is nothing but adding up infinitely tiny elements. So there are contributions from infinitesimal elements. And since here we have X hat times X hat, that's equal to 1. With 2 unit vectors coming together, that's equal to 1. And we have electric field times dA. So this is nothing but E times dA. The vector nature is gone now. And now we have to only talk about the magnitude of the electric field and the area of each of the elements. Electric field, since these are equidistant, we said these are the planar configuration. For planar configuration, electric field is a constant. So if it's a constant everywhere, it doesn't change whether you're here or here or here. Everywhere for each element on that surface, electric field is the same, which means that this can come out of the integral. Like for every element, the electric field is the same. So that comes out to be E times the area element integrated over the whole surface 4. Once it is only the area element I'm adding, what will I get if I add all the tiny surface areas? I'll get the total surface area of that surface 4. So that's nothing but E times, let's say A4, which is area of surface 4. Just for numerical purposes, let's emphasize that the numbers go through. So let's say the electric field here is equal to, it is in the X hat direction, and let's say it is 1.0 into 10 raised to 3 Newton per coulomb. That's a typical electric field. 10 raised to 5 is too large. That's when lightning happens. That's what sparks come out. If you are in a small lab, whenever you spark around, that means the electric field there is about 10 raised to 5. So 10 raised to 3 is the same electric field. And let's say this cube is of length L. So this is all of length L. L, which is the side of the cube. Let's say this is 1 centimeter. That's 1 into 10 raised to minus 2 meters. So what about the area? Now we are talking about the magnitude alone here. We don't have to worry about the vectors because we took care of the vectors here. So it is 1.0 into 10 raised to minus 3 Newton per coulomb. And the area is 1.0 into 10 raised to minus 2 meter. This is the square. The side of a cube will be a square of length L. So I have a square this. So that's my electric field times A. Oh, so this is plot. So then the 10 raised to plus 3, 10 raised to minus 2 square, that 10 raised to minus 4. So that's 0.10 to 2 sig digits because there were 2 sig digits in each of the numbers. And the unit is that of the electric field times the area, that's meter square. There is no special unit for flux, electric flux across a surface. So they will always work with Newton over Coulomb times meter square. Let's stick to this point here. So this is the electric flux across the fourth surface is E times A4. Let's now do very quickly the electric flux across other surfaces. So let's do the electric flux across the surface 1. Everything remains the same, except now we have to worry about what is the area element. Remember, this whole area is enclosed. So area element, this is, even though this is vertical, it can be the perpendicular vector could be to the right or to the left, but you have to go out of it so that dA will be here in this direction. It is perpendicular to the tiny element we are talking about, and it is coming out of the surface. Think of the surface as a closed surface, and it is coming out. That's why it is to the left, and this will be equal to, again, this time you sum over surface 1. This is equal to E times X hat dotted with. Now the area element everywhere on surface 1 is minus X hat times dA. So that's equals, this is equal to minus 1 this time. Everything else remains the same. It's the same electric field because it's uniform. It's like saying gravitational field on the surface of Earth, whether you're at 1 meter high or 10 meters high, it's the same field we are talking about. It's the same electric field we are talking about. And this somehow be equal to minus times the electric field itself, the magnitude of the electric field, which is the same everywhere. And this time it is the area of the first surface, but that's the same as the area of the fourth surface, which is L squared. This was also equal to L squared, right? So this was equal to plus E L squared. The idea is that the flux is going out of the box here, and in this case, it is going out onto the left, if you call it. In principle, it is coming in. the negative sign tells you that it is coming in. This negative sign means that the electric flux is going in. So that is more, so this is 4 will be equal to plus E times L squared. One could have also thought of this as the angle between these two vectors is 180 degrees, that the electric field is going this way. On surface 1, dA is going in this direction, and that's 180 degrees, and cosine of E dotted with dA is E times cosine of 180 degrees times dA. Dot product has this cosine of the angle coming in, cosine of 180 degrees is -1. That's the same as saying it is x hat dotted with minus x hat. Often cosine of the angle is also very useful. So that's good. A way of intuitively seeing this is that if you were to collect, if you have for example, a bucket in your hand, and this is a flowing river, and if you were to put it in this direction, how much water can you collect in there? Flux of water. Right here it is the flux of electric field. If you face it in the direction of the electric field, it will collect a lot of water. But if you were to face it in that direction, there won't be any. So negative is the extreme version. So only it can go into that. Here it is going on to the right. So that's an intuitive way of looking at this. In that spirit, now let's go ahead and calculate the electric field across surface Q. And that will be same idea, E dotted with dA. And now the dA associated with the second surface is going up. That's dA. That's a tiny element here, and the vector that is normal to that is perpendicular to that surface. So that's in the y direction. So this is equal to electric field times x hat dotted with y hat times dA. And this is the case everywhere. Everywhere on that surface, that's the case. And what is x dotted with y hat? The magnitude of x, which is 1, magnitude of y, which is 1, and angle between x hat and y hat. That's cosine of 90 degrees. Dot product is magnitude of the first vector, magnitude of the second vector times the angle between the two vectors. It is cosine of 90 degrees, and cosine of 90 is 0. So that's equal to 0. Everywhere on that element that is equal to 0. And that's where the vector nature of area is playing an important role. You couldn't have got this if you were just working with the area itself as a scalar. So that vector nature played an important role there. If this is equal to 0, everywhere this is 0, that whole thing is 0. That is a quantitative way of saying that there is no electric field line crossing the surface. All electric field lines are coming in from this face of the tube, and they're going out onto the right face of the tube. The same idea goes for 3 is equal to 0, and there is of course 5 and 6, but they are also perpendicular to the electric field. So flux about the fifth surface, which is not described there. And the sixth surface is also equal to 0. There is one interesting thing, other than the details of this concept that we have developed, that electric flux is the amount of electric field that, or electric field lines that crosses the surface. If you notice the total electric flux total, right? For this complete closed tube is equal to the flux of 1 plus the flux of 2, 3 plus 4, 5, and 6. And what is that equal to? If I add up all of this, that's 0, correct? So that's 0. And is there a significance of that? Why is it 0? And that's what we want to address now. Why is it 0? How can you make this non-zero? What is that total flux implying? Is that a physical understanding of that 0? Or whatever that comes out to be, it won't be always 0. The total flux of a closed surface, is there a meaning associated with that? So let's change this configuration a little. Keep this here. Or just intuitively speaking, how would you change this to non-zero? Maybe I can ask you guys, just geometrically looking at this. Field lines came in, went out. When will this be non-zero? Think of an electric field configuration when this will not be 0. How will you make this non-zero? Any answers, right? Okay, so okay, think of the following example. Let's say there is a positively charged plate. Okay, this is a connecting plate. Remember, there were 2 possibilities, right? The insulating plate and a connecting plate. There was a factor of 2 different. So it's just talking about connecting plate. And here sigma, it doesn't matter, it's just a uniform electric field. Here, that's your electric field lines. But on the left side, it's again positively charged. So if you place a positive charge here, it will repel it. You see the difference between them, that it is all facing in one direction and this is facing on both directions. And now remember that was an abstract view. This did not really exist. This was our thought process. We were thinking of a Gaussian surface. This is an abstract cube we built around it. It can intersect with all these plates because it's just abstract way of thinking of how much electric field lines go across it. And again, line out. And now if you notice, the A on this side is in this direction. The A in that on the left side is still to the left. That's the same, but electric field lines here is on to the right. Electric field to the left is to the left. So they're aligned with A dot with the A. And if you were to do this calculation again, flux of the electric field across the 4, 1, and so this will 4 will come out to be plus E times L squared. 1, this is the difference, this is a positive sign. Notice this came out to be negative there because now this will not be minus x hat, so this is also minus x hat, minus x hat, minus x hat gives you a positive sign, and that's E L squared. Rest everything comes out to be 0 because they are perpendicular. So Q 3, 5, and 6. That's all equal to 0. And the total flux now is equal to 2 times E times L squared. Let's think of the total or think of the electric field due to a planar charge. This was sigma over epsilon naught. And this will be on the x hat to the right, right? On the right side of the plane. That's sigma over epsilon naught. And sigma is charge per unit area. So it is Q over epsilon naught. Times, Q times sigma over epsilon naught times L squared. Sigma, remember, is charge per unit area. And for the region that is enclosed inside this Gaussian box, you can say this is Q times charge 2 over epsilon naught times sigma is charge per unit area and multiply by L squared. If it's a conductor, there will be charges on both sides because they will repel each other. So there's a surface area on the right, there's a charge distribution on the right, and there's a charge distribution on the left. So when you say charge per unit area, the total charge is twice that, right? There is 2 surfaces that it forms, but each of that area is L squared. L squared cancels out, and what we get is the total charge inside the box over epsilon naught. By earlier asked, we got a 0 earlier because there was no charge inside, and now it seems like the total flux that we can enclose is a measure of how much charge is there inside that surface, inside that closed surface. If that is really true, if this is not just a coincidence, we work with very simple geometry. If that is not really true, we should not, we should test this for more charges. So let's take another simple example. I said spherical symmetry is going to be another surface which will be very easy to work with. So let's do this for a point charge. Again, the suggestion seems to be the electric flux that is going out of the surfaces is a measure of how much charge there is inside that closed surface. So any closed surface, you just ask how much charge is there inside. If there is no charge, no calculation needed, you just take it 0. If there is a charge, it must be the total charge inside that up to a factor of epsilon naught, which is there in the denominator. And that's a suggestion. So let's see if this works for other geometries also. And if that is the case, then we will state it as a theorem. Let's say a point charge. We know the electric field due to a point charge, E is K times the charge itself over how far is the observation point times our path radially outward when the charge is kept at the center. I think of it as a sphere. So if I were to draw this, that's your positive charge, that's my field line. That's your field lines, and now we need a Gaussian box, right? I need an abstract box, but this time, since it is a spherical symmetric distribution, I won't use a box. Instead, I will use a sphere to enclose this curve. So that's fine. This doesn't really exist. This is not physically enclosing this charge. This is just an imagination that there is a surface around the positive charge. And that's right. This is so this is the Gaussian surface. It is specified earlier. I specified the cube by specifying the length of the cube. Here I have to say it is r. Let's say radius r. That means this is radius r. This is an observation point. This is true for any r. I could be here, outside, inside, anywhere, and I can calculate the electric field. Electric field is a measure of how much force a second charge will experience when I keep it at the observation point. So this is the distance of that positive charge, the second positive charge that I keep, and then I will know how much force it will exert, and will always be radially outward. But we are working with electric field, and we are asking how much electric field lines cross the closed surface. There is a source of electric field, and you are trying to capture all the field lines that is going across the surface, but the surface is enclosing that positive charge, so the flux. And this time it is the total flux, right? Because the surface, I don't have to specify 6 surfaces for a sphere. One surface, there is a lot of symmetry, and so just one surface is good enough. So often, to specify that this is a closed surface, so this is an integral, so that's a symbol, integral over a closed surface. That's a symbol that you will see often around. That means it is not the electric flux across its simple surface. That surface is a closed surface. It could have various geometry, but whatever it is, it has there is a bound to the volume that is contained inside. Electric field plotted with it. That's the flux, right? Break the surface, break the sphere into tiny elements. So this is the element we will talk about. So it has a three-dimensional nature to that. And whatever that surface is, that's a tiny element. That's your dA. That's radial output. That's dA, which is equal to it is radially outward because it's a sphere. It's a surface of a sphere is always perpendicular to the radius. So the normal to that tiny element will be along the radius. So that's our hat times dA. Earlier we said x hat times area because the direction of the area element was its hat. in this case, the direction of the area element is r hat. Flux equal everywhere on this surface. I have calculated the electric field. Electric field is K times Q. My observation point is on the surface of the sphere. So this radius R, which was for the observation point, this time it is on the surface of this sphere. So it has a radius R. So it's a special sphere. It's not any observation point. It is the sphere that I've drawn here. So I replace it with square. That's the particular surface we are talking about. And there is an R hat, which means it is always directional, always radially outward, right? For the point charge, electric field is radially outward. Area element, it is R hat times dA. I write it the vector first so that it encounters the other vector that is in the equation, and dA. Again, the same two vectors coming together. The area element is perpendicular, electric field is perpendicular. They have parallel to each other. So dot product of that will have the sign 0 in it. That's equal to 1. So the vector nature is gone. I'm integrating on the surface of this Gaussian sphere. Everywhere on that Gaussian sphere, K is the same. Charge is what is sitting inside, that's the same. It doesn't care whether I'm on this surface or any other surface. This radius R is the same everywhere on that sphere. So this R can come out, and this is equal to 1. So what I have here is K times 2 over R squared times, now it's a scalar. It's not a vector area we are talking about, it's a magnitude of area that we are adding up now. And that's equal to the surface area of a sphere that we know. The scalar nature of that area is 4 pi R squared. Notice that this integral is usually very complicated. It's only for a sphere and for a plane that this comes out so simple. And sometimes for a cylinder also. As far as the radius is the same, then everything comes out of that. And this piece coming out plays a very important role. If you were not able to do that, this integral is very hard. As simple as if this point charge was not at the center of the sphere, if I shift it even a little bit to the right, the symmetry is gone, and then you cannot do this integral very easily, at least the way we did this. We just argued that this goes out of the integral, and what is remaining is just an area. That argument doesn't go through, so it depends a lot on the symmetry of the problem. So that's the challenge when working on problems like this, that in certain problems it's very easy, and the moment we make a small change, this becomes exponentially harder. Nevertheless, in this case, the total area is 4 pi R squared, and this is K. Let me divide that. So, square times dA. That's, I said, this is a scalar of the magnitude of area is coming in. The vector nature is gone. Magnitude of this tiny element, and then you add up all the elements on the surface of a sphere. That's the surface area of a sphere. And that's 4 pi R squared. And then notice a very fine thing that is happening. The radius square cancels out. Exactly cancels out. And what you have here is, say this is K is 1, or let me say this is K and 4 pi times Q. But K itself is 1 over 4 pi epsilon naught. That is a 4 pi times Q. and that's equal to Q over epsilon naught. Compare this with what we said earlier, and the total flux inside that square, our suggestion was that it will bring out the total charge inside the surface divided by epsilon naught. Here, the geometry is not as straightforward as a square, but still that cancellation happens. It doesn't matter which sphere I'm talking about. I could have it very close to the sphere. I can take this R as close as I want to that point charge. I can be infinitely close to it, and still, because the cancellation happens, it will always be Q. I can go very far away, still it will be the charge Q. All the field lines will collect together, always they will add up to epsilon naught. And if this is really true, this also tells something very special about our dimension of our world. Sometimes you will hear that is the dimensions of our space really three? That means to say, are we living in a three-dimensional space? That means there is an x direction, there is a y direction, and there is a vertical direction. Is there a fourth dimension at all which we are not able to sense? If we are not able to sense, it may not be really there, because this cancellation requires the dimension of the space. It is those 4 pi r square that canceling out with the electric field. So there are two possibilities. Either the electric nature of a physical quantity does not go into the fourth dimension that we often speak about, or our dimension of space is really three. It cannot be more than that, at least to observable content. And this theory has been tested to 13 significant digits. Remember, so to the accuracy of 13 significant digits, we can say that the dimensions of our space is really three. At least the electric field does not go into the fourth one to that much accuracy. If it is there, then at least electric field will not go in. So most of the theories that you will hear about, most of the exotic theories that we won't study here, which often talk about extra dimensions, they will always say that electric forces will not penetrate them. It is always a gravity that goes into the fourth dimension, or how much other dimensions you want to go. But the electric forces typically keep confine it to the three dimensions. So that's something extra. What we want to take home from here, we want to make this a law, or Gauss made this a law. So this is called Gauss's law. Okay, then the next step. It says that the total flux, or this is the total flux of understandable, the flux across a closed surface. Pick any closed surface that you want to. For example, here, right next to you, construct a small closed surface. It doesn't have to be spherical. We talked about a spherical surface and a cubical surface, but Gauss made this a law. This conjecture is that take any surface, a closed surface, this will always give you the charge enclosed. That means whatever charge is inside the surface. If there was another positive charge, the electric field is hard, but or has a complicated structure there, but it is only the charge that matters, divided by epsilon naught. And the moment you take it, lift it to a law, then you can use that. Till now, we were calculating the left hand side and trying to calculate what the right hand side is, but often you know exactly how many charges are there. So you can talk about what the total electric flux is immediately if you know the right hand side. For example. So let's have a configuration. Let's say positive and negative. And this keeps going, or it doesn't matter really, but let's say that this keeps going in all directions. And even better, you can say it keeps going in all directions. Let's say now I have to make a Gaussian surface. Let's say that's my Gaussian surface. And this is plus Q, Q minus Q, plus Q minus Q, plus Q minus Q, and so on. And if I'm going in all directions, let's say this is thin enough that this is only one layer thick. Right? So let's see also specify this is one layer thick. That means it encloses only the charges in that one layer. And you could ask, what is the flux on the surface X? So what is the flux in that surface? It's a closed surface. So it's enclosing the four charges, and on top there is a cylindrical face or a circular face on top and bottom. But it's a closed surface. So I immediately say this is epsilon naught and just count the number of charges inside. That is a minus Q, plus Q, minus Q, plus Q. The four charges get saying it's all the same, it's zero. That means the total electric field that is going, so some of the electric fields will be coming in, some of them will be going out. If you add up all of them, this has to be equal to zero. It will be very hard to calculate that. Imagine you want to calculate the electric field at every point, it will be very hard and very tedious, but it will come out to be always zero because of this reason. We'll come in and talk about more non-trivial scenarios, especially with symmetry, and extend this further. Thank you. Recording work. Yeah.
It should have to. Do I like end the meeting or do I have to do anything
Just
special?
end the meeting and then it will send me an email.